Welcome, students. So, we will continue our discussion on block codes. In the last lecture, you saw how we were using LDPC codes and how we were decoding iteratively received code word using the LDPC decoding algorithm. So, today we will go through the last topic under your linear block codes, which is basically block interleaving, and then we will move forward with another type of codes which is called convolutional codes, and that will conclude the discussion about your error correcting codes. So let's see what is block interleaving. So block interleaving, this is a process which is related to your block code. So as the name suggests, block interleaving. So let's see what is a block interleaving. So usually what happens is that when your data is written and read from memory, so they are done in different orders. So if you recall your concepts that you learned in your microcontroller course, there was a concept called serial communication. So usually the data in any digital device is stored, all bits together, in a byte form or a block form, and you had to convert them from parallel to serial, and then each bit was transmitted serially, one by one. So usually, in any digital system, data is written to and read from the memory in different orders. So in case of your block codes also, your data is divided into different frames and blocks. So usually the data bits and the corresponding check bits are interspersed with bits from other blocks. So at the receiver, data are interleaved, or sorry, de-interleaved to recover the original order. Okay, so interleaving and de-interleaving, these two terms actually come together. So interleaving means, putting together uh, a given format of data, and in a specific way or in a specific order, and de-interleaving means to do just the opposite. Okay, so in case of your block codes also, you have seen that you have the data blocks and then you have the check bits. Okay, so this was your k bit message, and then you had this n minus k bit, you know um, check bits, and then the total frame was n bit long. So you are basically interleaving these two blocks together, and then in the receiver you have to de-interleave to recover the orders. Okay, so but in general communication systems, there are burst errors. Okay, so burst error means errors come in a burst, or they come together. Okay, so at a stretch multiple bits can be affected by burst error. Okay, so if this is your entire bit stream, let's say if you take a random bit stream, a very long bit stream like this, and so on. So a burst error means an error that may affect, let's say, these four consecutive bits. Okay, so there is a burst of error. An error can be individual also, let's say only this particular bit is affected, or this particular bit is affected. But in case of burst error, um, multiple bits can be affected together. Okay, so burst error may occur, and this may spread out over a number of blocks. Okay, so these blocks, this is one block, let's say, and then you have another block, okay, where you have the k bit data and n minus k bit check um, check bits, and then you have multiple blocks interleaved together like this. Let's say this is block 1, this is block 2, and so on. And now if a burst error happens, let's say at this instance, then it might affect both these blocks. Okay, so if that happens, then error correction, you know, becomes very difficult. Okay, so that's why you need to do block interleaving. So let me go through the concept with this diagram. So let's say your data is read in this in this way, in from this side. Okay, so read encoded bits from encoder. So um, you can see, so these are the different blocks here. Okay, and it is read out one column at a time. So these are basically your n bits, okay, of the data. Okay, I mean, sorry, the n bits of the entire frame, where you have, you know, k bits of data and n minus k check bits. So k data bits and n minus k check bits, and then you have multiple blocks. So this is the first block, this is the second block, and so on. Okay, so you have the first n bits comes in the first block, then n plus 1 to twice n comes in the second block, then twice n plus 1 to thrice n comes in the third block, and so on, where you have m such blocks. Okay, so there are m rows. So the final row has mn minus n plus 1 to mn bits. Okay, so this is the way that they are you know, read in from this side and read out from this side. Okay, so now now why this thing is done. So this is the block interleaving process that I was trying to say. So why this is done? This is done to, you know, get rid of this burst error. So let's see what happens. Let's say you have a burst of error which affects this first 3 bits of this first block. Okay, so this is a block with n bits, where k data bits are there and n minus k check bits are there. So the first 3 bits are affected by the burst error, as I was saying in the previous slide. So now, if so, burst noise affecting 3 consecutive bits. So if I am reading from this side, okay, I'm reading. So when I'm reading, originally the data is encoded in this fashion. So you have this entire block where you have k data bits and n minus k check bits, but it is read from this side. Okay, this one is read first, this block. Instead of this block is read first in the, when it is read out, then this block. Okay, then this block. And the reason this is done, okay, the reason this is done is just to get rid of the burst error. So the burst is affecting these 3 consecutive bits in the original frame, but when you are reading from this side, your effective frame would look like this. Okay, so you are reading from 1, then n plus 1, then twice n plus 1, and finally in this way mn minus n plus 1. So this is the actual block that you are reading. Okay, and here you see only 1 bit is affected by the burst noise. Okay, when you are reading. So next block you are reading is this one. Here also only 1 block is affected. Again, the next block you are reading is this one, where also you have only 1 block affected by error. So this can be corrected efficiently. So instead of having 3 consecutive errors, you know, you only have 1 error per block if you are reading in this fashion. Okay, so that's why we are doing block interleaving, and the basic advantage of block interleaving is to spread out the effect of this burst noise, so that in each read out block you have only one error, and one error can be easily corrected, by block code, Hamming code with, let's say, d mean equal to 3. So if you go back few slides, so let me go back a few slides just to you know revise one particular aspect of these block codes. So if I go here in this slide, you can see that your dmin is 3, and this dmin, if your dmin is 3, then you can correct a single error. Okay, so this is a single error correcting code. Okay, so one error can be easily corrected using a code which has a dmin of 3. Okay, so that's why we are doing block interleaving. So now again, going back to the discussion of the block interleaving, essentially what we are doing by block interleaving is that we are allowing one error per block, and this can be easily corrected by a single error correcting code, as you saw, with dmin equal to 3. Okay, sorry, dmin equal to 3. If you have 3 consecutive errors, then you need a more complicated code with a higher dmin, and sometimes it becomes very difficult to even correct these type of burst errors. So that's why we are doing this bit interleaving. So only one bit in each data block is affected, as you can see here. Okay, so we'll move on, and that was the end of the linear block code discussion. Now we will learn about a different type of code called convolutional codes. Okay, so unlike block codes, these convolutional codes, they generate redundant bits continuously. Okay, so and usually they are small. Okay, you know in your block code, you are having n and k. So n was like 12 bits and k was 8 bits. So you saw one example that we solved where you are having a 12-8 Hamming code. You can have an 8-4 Hamming code, 7-3. So usually the block lengths are large. In case of your convolutional code, we usually take a few number of bits. Okay, so the number of bits in your data usually is of the order of 2 or 3. Okay, and then you have 1 or 2 redundant check bits, and then this process continues for the entire stream of data. So this is basically a more dynamic form of coding. Okay, so you are generating the check bits very fast and very dynamically for each of the 2 or 3 bits of the original message. So if your message is like this, let's take a random example. So 1010011100101, etc. Okay, so what you are doing in case of your linear block codes, you are probably um, selecting a large number of bits. Let's say 1 2 3 4 5 6 7 8. Okay, so these were your k, so these were your data bits, and then you were appending another, let's say, 4 check bits to make it a 12-8 code, and then you are sending it, and then you are taking the next block and sending it, and so on. In case of your convolutional code, you are taking, let's say, only two, or may at most three, and then based on these 3 bits you are generating 1 or 2 check bits, and then using that check bits as your redundant um, coding bits, and then in the receiver you decode the messages based on those 1 or 2 check bits. Okay, so this is more fast and more dynamic in nature. Okay, so usually um, these convolutional codes, other than the usuals n and k, there is another parameter, capital K, which is basically a constraint factor. So I will get back to the discussion of capital K in the next slide. So so K, as I just said, the small k and small n are generally very small, as I was saying, for convolutional codes, and the n bit output of this convolutional code depends on the current block of k input bits. So small k is the input bits, okay, um, and the previous capital K minus 1 blocks of k input bits. So what does that mean? So let's see with this example. So basically convolutional encoder is implemented using these shift registers and this modulo 2 additions. Okay, so this capital K basically tells you how many shift registers that you are using to generate your convolutional code. So in this example, your capital K is 3, and you are taking small k bits as input, and then let's say this is your convolutional encoder, and you are outputting n bits. This part conceptually is same as the linear block code part, where you are having k input bits and n output bits, and the encoder was actually um, mapping the k input bits to generate the n output bits, where out of this n there were n minus k bits which were the check bits. Okay, in this case also we have the same scenario. So you have k input bits here, so, I mean small k, and you have n output bits. The only difference is that this small k and small n in case of convolutional encoder is usually small. Okay, so in this example your small k is 1, okay, and n is 2. Okay, so this is an example of a convolutional encoder with 2, 1, 3 as its parameter. So 2 is the output bits, 1 is the input bit, and 3 is the number of shift registers that are used to implement this encoder. Okay, so basically your bit streams are coming, let's say 1 0 1 1 0 whatever, and each bit is getting input to this convolutional encoder, and for each bit you are generating 2 bits that are output, and that is sent through the channel. Okay, so this is an example of a rate half convolutional coder. Okay, because every 1 bit is converted to 2 bits um, as a means of the coding procedure. Okay, so you can have rate 1/3 also, rate 2/3, many combinations can be possible. Okay, so let's focus on this particular example and how this works. So if you see closely, so let me, yeah, so if you see, whatever input bits are coming, those input bits are loading these shift registers. Okay, so if your input bit is, let's say, 1, then this shift register will be loaded with 1. Okay, let's assume the initial state of all the shift registers are 0. Okay, so initially all of them were 0, and then if a 1 comes here, then the state becomes 1 0 0. Okay, so based on 1 0 0, whatever will be the output of this modulo 2, okay, so that will be the vn1 here. Okay, that will be the first bit of the two output bits. So in this case, this vn1 will be the modulo 2 addition of 1 plus 0 plus 0. Okay, so that will be actually 1. Okay, and then this vn2 is the modulo 2 addition of un and un minus 2. So this will give you 1 plus 0. This will be also 1. Okay, so these will be the two output bits if your input is 1. Okay, so in this way, if your input is 0, I mean the next input is 0, by that time this 1 will be shifted here, because this is a shift register, and here you will have a 0 as input, and this will remain 0 from the initial loading, and then whatever be the state of the shift registers, those will contribute to the output. So in now you will have 0 plus 1 plus 0, which will be 1 again. Okay, so the output will be 1, vn1 will be 1 again, and vn2 will be 0. So in this way the output changes, and this input output relationship can be represented by this state diagram. Okay, so what this state diagram does, okay, so let's say your initial state is 0 0. Okay, so whenever in the 0 0 state your input bit is 0, so input bit 0 is represented by the by the solid line, and input bit 1 is represented by this dotted line. Okay, so 0 0, let's say your un minus 1 and un minus 2. So whatever you are inputting is coming straight to this shift register, which is marked un. Okay, so that is your input. Okay, so when you say 0 0, it basically means the state of un minus 1 and un minus 2. So let's say the initial state is 0 0, which is marked by a, and these two are 0 and 0. Okay, so now, as I was just saying, when you have input as 1, okay, so this will be this output will be 1, because this is the vn1 is the modulo 2 addition of all these three, and vn2 will be also 1. Okay, so when you are in a state 0 0 and your input is 1, okay, then your output will be, sorry, yeah, your input is 1, so your output will be 1 1, as I was saying here. So the output will be 1 1, and it will move to the state 1 0. Okay, why? Because at the next instance, so let's say this is step 1, where you have an input 1. At step 2, these will be shifted 1 plus, and un will be un minus 1, and un minus 1 will be un minus 2. So the next state will be 1 0, because we are counting the status of un minus 1 and un minus 2 to count the states. So the next state will be 1 0. So when at state 0 0 your input is 1, which is represented by this dotted line, because dotted line signifies input 1, then you reach to the state 1 0, okay, with an output 1 1. So this is your output. Okay, now if your input is 0 here, okay, if your input was 0 at this state, let's say let's cut this out and put a 0 here. So if your input was 0, then the output will be both the output will be 0, because you are doing the modulo 2 addition of all these three for vn1. So vn1 will be 0 and vn2 will also be 0. So at state 0 0, when your input is 0, which is signified by this solid line, then the output is 0 0. Okay, that's what we have got. And it goes back to the state 0 0, because this 2 0 0 will be now shifting one place in step 2, and then this will be 0 0. Okay, so in this way, if you work out the transitions from the other states, you will find that you can complete this entire state diagram. So basically, at each state, whenever there is a input of 1, then it will move to a different state, or it can still remain in the same state. Okay, it depends, it all depends on these relationships. Okay, and these numbers signify the output. So let's say when you are in state 0 0, and if your input is 0, then you remain in the state 0 0 with an output 0 0. When you are in state 0 0 and your input is 1, you go to state 1 0 with an output 1 1. Okay, now if you are in 1 0, let's say let's analyze the case for 1 0. Okay, so let's say um, let's say let's say if we have 1 0, then what will happen? Okay, so here let's say 1 0, so we are in state B. Okay, and at state B, let's say if your input is 0, okay, if your input is 0, then the output will be the modulo to sum of all these three, so the output will be 1. Okay, so let's say your vn1 will be 1, and vn2, let's see what your vn2 will be. Vn2 will be un minus 2 plus un, so this will be 0. So when your state is 1 0 and the input is 0, your output will be 1 0, and you will move to the state 0 1, because these two will now shift to here. So let's verify that. At state 1 0, if your input is 0, which is denoted by this solid line, so this is the case here, then the output is 1 0, we have got this, and it goes to the state 0 1. Okay, so this is the state 0 1, which is labeled as C. So in this way you can work this out, the entire state diagram. And the state diagram represents the encoder, the convolutional code encoder, and in other way, the encoder can be represented by this state diagram. Okay, so now if you if you look into the state diagram, it might look very clumsy for a very large number of states. Okay, so let's say here you have 3 shift registers. Okay, so your states are denoted by like 2 bits. Okay, so if you have capital K as your number of shift registers, then each state has K minus 1 bits, so 2 bits are represented for each state. Okay, if your K is large, let's say if your K is 4, then you will have each state denoted by 3 bits, and you will have 8 possible states. Okay, here since each state is denoted by 2 bits, you are having 4 possible states, if it is denoted by 3 bits, then you will have 8 possible states, and then the state diagram might look very clumsy, okay, and it will be difficult to work with that state diagram. So that's why, to make things easier, what is done is you define a trellis diagram. So this diagram, this might look complicated also, but this is easier to work with. Okay, so this is called trellis diagram. So I will explain this part by part. So let's say these were the 4 states that you had, okay, as you saw in the previous slide: A, B, C, D. So A is 0 0, B is 1 0, C is 0 1, and D is 1 1, right? So if all the state transitions, okay, instead of drawing it in this fashion, where the next state um, is denoted by an arrow like this, a directional arrow like this. So from A, which is 0 0, when your input is 1, you are going to state B. Okay, so this is denoted by this arrow. And then from B, when your input is 1 again, you are going to state D, with denoted by this arrow. So these state diagram, each transition of the state diagram, if you just extend on the time axis, so this is the initial time t0, okay. So at state A, let's say at t0, you are in state A, and state A is 0 0. Now from state A, you can have an input of 0 and you move to state A again. Okay, so this was denoted by this loop here. If at state A, if your input is 0, then you have an output 0 0, and you remain in the state A, or you loop back to state A. In the trellis diagram, what you are doing is that, let's say at t0 you are in state A. Now at t1 you can remain in state A if your input is 0, or you can go to state B if your input is 1. Okay, so these are the two possibilities that you can have if you start from state A. Okay, now let's say at t1 you can be either in state A or state B, depending on whether your input was 0 or your input was 1. And also one more thing is featured here: if your input is 0 at state 0 0, then the output is 0 0, and if your input is 1 at state 0 0, then your output is 1 1. So the output is denoted by this slash. So this is the input and this is the output, okay, separated by this slash. So at t1 you can either be at state A if your input was 0, or state B if your input was 1. Okay, now from t1 to t2, again, if you are in state A, you either remain in state A or you can go to state B. If you are in state B, then you can go to state C or state D, depending on whether your input is 0 or 1. So in this way you complete this trellis diagram. So you see we have maintained the same type of notations here. We have A equal to 0 0, B equal to 1 0, C equal to 0 1, D equal to 1 1. So these are the states. And then we have also followed the scheme that if your input bit is 0, then that transition is denoted by this solid line, and if your input bit is 1, then that transition is denoted by a dotted line. Okay, so we have maintained that also. And then if you go on from t0 to t1 to t2 to t3 along the time axis, then you will have a diagram like this, okay, which is called a trellis diagram. Okay, so here we are stopping at t7, but you can keep continuing this theoretically to infinity. Okay, so so what is the advantage of this trellis diagram? Now we will see. So so if you are trying to encode some bits, okay, based on the convolutional encoder, the example of which you just saw in the previous slide. So let's say this is my convolutional encoder, and this is the state diagram of this encoder, and we have represented this state diagram using this particular trellis diagram. Okay, so now let's see how the encoding procedure happens, or how we can use this trellis to find out the coded output bits given an input message bit. So let's say your input message is 1. Okay, so if your input message is 1, and let's say we are starting from t0. Okay, so in that case you will move through this arm of the trellis, because you are assuming that you are now at state 0 0 at time t equal to t0, and your input message is 1. So if your input is 1 at state A, then your output will be 1 1, and you move to state B. Okay, so the coded output in this case will be 1 1. So this will be your output. Okay, now let's say at t equal to t1 you are here, and let's imagine that the next input message bit is 0. So in that case it will move through this path of the trellis. So here the input is 0, and it moves to state C with an output 1 0. So the coded output will be 1 0, because your input is 0. Now let's say the next input bit is 1. Okay, and you are at state C at time t equal to t2. So from state C, if you have an input 1, then you transition to state B with an output of 0 0. Okay, so this is the path that you will be following, and the coded output will be 0 0. Now let's say the input is 1 again, and we are at state B here. So at state B, if your input is 1, then you go to state D with an output 0 1. Okay, so the coded output here will be 0 1. Okay, and at t equal to t4 you are at this state. Now again, let's say your input is 0. So from state D, if your input is 0, you go to state C with an output 0 1 again. Okay, now at t equal to t5 you are at state C here, and let's say your input message is now 0. So if your input is 0, then from here the path that you can follow is this path. Okay, so that's exactly what you are doing, and the output will be 1 1. So the output here is 1 1. Okay, and you are at state A again at time t equal to t6. Okay, now let's say your input is again 0. So you are at state A now, and if your input is 0, then you stay at state A with an output 0 0. So here will be your output 0 0. So this is if this is my entire message string, then according to this convolutional encoder, we have figured out that the coded output will be this. So for a message stream of 10110000, the coded output will be 11100001011100, like this. Okay, and you can proceed further. If you can stretch the trellis further in this direction, and you can proceed further. Let's say at t equal to t7 you are at state A, and now whatever the input bit, next input bit here, According to that, you move along the trellis and you can find out the coded output. So this process actually goes continuously and iteratively. As long as you are getting messages from a transmitter, you can use this convolutional encoder, uh, using this uh, using this type of circuitry to to code each input bit, and then have the coded outputs like this. So this code is an example of 1 by 2 or rate half convolutional coder. You can have rate 1/3, rate 2/3, and accordingly your trellis diagram will look a little different, but the basic concept remains the same. Okay, so now if we move on, so that what you saw was the encoding process. So you were encoding each message bit uh, using the trellis diagram. Now what what would happen if you want to now decode, like if you receive a long code word and you want to decode, then what will happen? You can use the same trellis diagram, but now you use a algorithm called Viterbi algorithm. Okay, so this is an algorithm which is very famous. This was actually discovered or invented by Viterbi. This is named after its inventor, Viterbi, and this person was a famous engineer who was associated with uh, the University of Southern California. Okay, so if any of you go to USC, and if you study engineering, you will be studying in the Viterbi School of Engineering. So the School of Engineering in USC is named after Viterbi, and this is a very simple algorithm, but at that time nobody thought about it. So Viterbi was the person who came up with this very intelligent algorithm to decode a convolutional coded long code word into its original message. So we will see um, the Viterbi example of the Viterbi um, algorithm, but the question would rise that why are you using an algorithm for decoding? Like, can't we just use the Hamming distance and check which which the received code word is close to which of the code words? But this is not possible for a very large set of code words. Okay, so if you have a 4-bit message, okay, then you have about 16 code words like this. Okay, and if you want to check the Hamming distance for each of the 16, it takes a lot of computational um, power and a lot of time, a lot of computational time. So for long messages, the number of code words will be even larger. Okay, so it is very inefficient to look up for each of this code word and then try to see if your received code word is closer to one of these. Okay, so that's why you need an iterative algorithm. Okay, and Viterbi algorithm is an iterative algorithm. Okay, so I will again take the example of this same trellis diagram and the same convolutional encoder that we that we showed before, and see if we have a received code word like this. Let's say this is the received code word, this entire number of bits, okay, 1110 1100 011001. And if you want to decode this and find out the original message applying the Viterbi algorithm, then what will be the procedure? So let's see. So I will explain you the Viterbi algorithm with this trellis diagram, and I will show you how this received code word is decoded. Okay. So so this was originally a rate half code encoder. We are using the same example, same convolutional code. So that was 1 bit was input and 2 bits were output. So your code word here, you can you know you can separate them into 2 bits each, okay, because the output is 2 bits, and whatever received code word you have can be separated into 2 bits each, okay. So if you separate them into 2 bits and then you write it in this manner, so this is your trellis diagram, and you write these 2 bits, each of these 2 bits of the received code word along this trellis, where this combination of 2 bits fall within the transitions, like from T0 to T1, T1 to T2, T2 to T3, etc. Okay, and then let's see what's happening here. Let's go across the trellis from this state, from this initial time t equal to t0. Okay, so at t equal to t0, if you move along the trellis, okay, you can have only 2 paths, okay, either this path or this one. So these are the 2 paths shown using the green arrows, okay. So now just compare this part, these 2 bits of the received code word, with the possible outputs that you can have if you go through these 2 paths, okay. So this is the output and this is the input, okay. So let's focus on the output, okay, and compare this output with these 2 bits of the received code words, okay, and let's find out the Hamming distances. So if you follow this path, then the Hamming distance will be 2, okay. If you follow this path, then the Hamming distance will be 0, okay. So you write down these values here at t1, okay. So if you have reached t1 from t0 by taking this path, then the path length would be 2 based on the Hamming distance, and if you had taken this path from t0 to t1, the path length would be 0, okay. So now the idea is to keep the shortest path. So this is the shortest path according to the Hamming distance, because this and this exactly matches, and therefore the Hamming distance is 0, okay. So let's proceed one step more. If you had followed this path, okay, and gone to t2, from t1 to t2, here you have these 2 bits from the received code words. So here, if you check only these 2 outputs, then the Hamming distance is 1. Previously it was 2, so 2 plus 1 is 3 here, okay. So you are accumulating the Hamming distance. If you had taken this path, then the Hamming distance is also 1, between 1 0 and 1 1. So you would have accumulated one more point here, and you would have end up in 3, okay. On the contrary, if you had followed this path, okay, from t1 to t2, so here you are accumulating no points, because this one is same as this one, so there is no Hamming distance or 0 Hamming distance, so you still keep 0. And if you had followed this path, then the Hamming distance is 2, between 1 0 and 0 1, and then you will have a plus 2 if you had taken this path. So this will be your accumulated path length. Okay, so you can see that if you had taken this path, your path length is increasing. If you had taken this path, I mean this particular path from T0 to T2, this one has the lowest path length. Okay, so basically you will follow this path from now on. Okay, you will discard the other paths. Okay, because these paths are are taking you longer. Okay, or these paths itself are longer in length as far as the Hamming distances are concerned. So you don't want this path, you want to take the shortest path. So you keep following this path, because until this point this is the shortest path that you got starting from T0. So now if you go from here, there are two possibilities from here. If you go along the trellis, so either you can take this path or this path. Okay, so if you take this path, and then you can see that these 2 bits of the received code word exactly matches with the output here. So the Hamming distance is still 0, so here you will have the accumulated path length as 0, and here if you take this path, then the Hamming distance is 2 and the accumulated path length will be 2. Okay, so it was 0 here, so 0 plus 2, and here you have 0 plus 0. So you have 0 here, you have 2 here. Okay, okay. So let's look a little further. So let's say if you had taken, just for your, just for verification, if you had taken this path, okay, these two at T2 was very long, so the accumulated path length was 3. This was the shortest, but this was the second shortest. If you had taken the second shortest, then by the same logic the accumulated path length would have been 3 here, 3 here. So basically we don't want these paths. Okay, this is up to this point, this is my shortest path. Okay, if we had taken this route. Okay, so I will proceed further with this path, and again check the Hamming distance with this particular 2 bits here. So this is 0, so this still remains 0. This is 2, so the accumulated path length becomes 2 at this stage, because we are adding plus 2. And if we had taken, let's say, this path, then the accumulated path length would have been 3. Okay, so this is still the shortest path. Okay, so now if we go on further and keep doing the same steps, okay, that is to calculate the incremental path length based on the Hamming distance, and then adding that to the previous values, we will get the total distances. So these two paths are still giving you 1 as the accumulated sum of the path lengths. If we had gone through the other direction, then this would be larger, so we will discard those. We don't need this one and this one. So we can go along this path or this path with an accumulated path length of 2 and 2, or we could have taken this where we would have accumulated path lengths of 1 and 3. Okay, so this gives me, now at this stage, this gives me the shortest path. Okay, so up to this stage we were having this as the shortest path. Now the shortest path is this one. Okay, so now if we just move from this point, you will see that now for both these paths the accumulated path length is 2. Okay, so this is your shortest path shown in red, or it could be this one as well. So starting from T0, to T7, the path that is marked bold with red, that's your shortest path. So it is either this one or or this one. So any two path is possible. So now we were supposed to decode this received this entire received code word, right? So the decoding will now be very easy. Now that you have found the shortest path according to the Viterbi algorithm, you just follow this route back, okay, to the original this source, okay. And while following this route back, whatever is the input, that was your actually the original message. So here your decoded message will be this one, okay. So let's verify. Let's say I choose this path, okay. So this decoded message will be 1, okay, and then 0, okay. So 1 0, then this one is 0 0 here, then this one is 0. So we are just taking the inputs here. Then this one is 1, so 1, and then this one is 0, so 0 here, and then finally this one is 0, so 0. So this will be your decoded message, okay. Or in other words, if this was your input, then you would have followed this path through the trellis, okay, as you saw in the case of encoding. So we are just finding the path using the Viterbi algorithm, and then we are getting back the original message, okay. So so I'll stop here for a while, and I will show you a video on Viterbi algorithm to get the concept more clearer. I mean, this is a video that I found from the internet, so that video will play now, and you please go through that part, and I'm sure you will enjoy watching that video, and your understanding about the Viterbi algorithm will become more firm. Okay, so I will stop here for a while and play the video for you.
Hello, my name is Keith Chugg, and I'm going to provide a very quick summary of the Viterbi algorithm. So I'm going to do this through an example of planning a road trip from the west coast of the United States to the east coast. And the way I've done this is I've considered 4 possible cities that you could start with on the west coast: Seattle, Newport, San Francisco, and Los Angeles, which I've labeled USC. And I only want to drive less than 750 miles a day each day. So, for example, at the end of the first day, this leaves me with 4 possible cities: Boise, Salt Lake, Las Vegas, Tucson. And in the third day, it's the pink-colored cities of Casper, Denver, Albuquerque, El Paso, etc. And so this would take me 7 days, and each day I would drive less than 750 miles. And the problem I want to consider is, what's the shortest way to go from the west coast to the east coast? So I know it's going to take 7 days, but I want to drive the least amount of mileage. Okay? Let me get rid of the background, and then you can see this diagram a little more clearly. So this diagram is called a trellis diagram in the context of Viterbi decoding, and it's basically a diagram that shows all the possible routes you could take from the west coast to the east coast under this 750 miles a day or less constraint. So one way you could solve this problem of finding out what the shortest path is just to make a long list of all the possible routes that you could take and take the sum of their 1 day mileage to get their total mileage for each of the routes. Now there are a lot of these paths, so that's really what the problem is. So for example, if you consider just that you're in Salt Lake, there's 3 ways to leave Salt Lake. One is Casper, the other is Denver, the other is Albuquerque. There's 3 ways to leave Casper. There's 3 ways to leave Denver. There's 2 ways to leave Albuquerque. So if you just look at after 2 days of traveling, leaving Salt Lake, you're up to 3 plus 3 plus 2, or 8 different routes just in those 2 days. And then if you consider extensions of those routes from the ones from Pierre, Lincoln, Amarillo, etc., the number of possibilities keeps to grow very rapidly. So it's really not practical to write down a list of all the possible routes. There's got to be a better way. And in fact, there is a better way to do this, and that's exactly what the Viterbi algorithm does. So I want to try to explain the core ideas of the Viterbi algorithm and the execution of the algorithm using this toy example. So the way to think about it is to first sort of condition on one potential city. So let's focus on Boise. Now what I want to illustrate is if I say, if I just hypothesize that the best way to go from the West Coast to the East Coast goes through Boise, then I can kind of break this shortest path problem into 2 segments, namely a segment to the left of Boise and a segment to the right of Boise. And to illustrate this, I'm going to provide a little bit of side information here that I happen to know. I happen to know that the shortest path from Boise to the East Coast is colored in here, the one colored in here by this green crayon. So it goes Casper, Lincoln, Kansas City, St. Louis, Pittsburgh, Washington, and that's 2,685 miles total from Boise to Washington there. Okay, so the idea here is that regardless of how I arrive at Boise from the West Coast, whether I came from Seattle, Newport, or San Francisco, the best way to go from Boise to the East Coast is still this green crayon line, and it's still 2,685 miles. Okay, so now you can very, very quickly reason that you really don't need to consider Newport, San Francisco legs to Boise, because Seattle to Boise is shorter. In other words, if you were to claim that the shortest path to go from the West Coast to the East Coast, passing through Boise, started in San Francisco, I could counter that argument by saying, well, let's start in Seattle and go to Boise, and then we both follow the green crayon path from that point forward, and clearly mine will be less, the path from Seattle will be less than the path from San Francisco, because it's 494 miles from Seattle to Boise, and it's 648 if you start in San Francisco and go to Boise. So this allows us to eliminate the paths that go from Newport to Boise and San Francisco to Boise, and just keep the shortest path from the West Coast to Boise, which is Seattle. So by considering conditioning on the state of being in Boise, we decouple the problems into 2 shortest path problems. One is still hard. That's the green crayon one that I gave you the answer to. The other one is very easy. It's just the shortest way to go from the West Coast to Boise, and that's a very simple calculation. We can all tell that's Seattle. So we repeat this step at Salt Lake, Las Vegas, and Tucson. So Salt Lake only has one, Tucson only has one way to get there from the West Coast, and Las Vegas would just be a simple comparison between the way to get there from USC and the way to get there from San Francisco. And of course, USC is going to win out because it's 275 miles. So after one step of the Viterbi algorithm, this is the status. We know the shortest path from the West Coast to each of the day 1 destination cities. And we've also kept track of what those best paths are. Those are the lines with the arrows. And the mileage of those best paths at each of the cities. Those are the yellow numbers near the cities. Now let's repeat this over and over, and that's the Viterbi algorithm. So now let's first go and condition on Casper at the end of day 2. Okay, so we need to find the best path from the West Coast to Casper, and we can tell that that has to be the one coming from Boise or Salt Lake, and there's only 2 of those because we've eliminated the other paths coming from, for example, Newport, San Francisco, going through Boise. We already got rid of those. So we really only need to consider the 2 paths, which are the extensions of the arrowed paths, and we add on the 1-day mileage for each of those. So for example, if it came from Boise, it would be 494 plus 669. If it came from Salt Lake, it would be 748 plus 402. So we need to compare those 2 sums and choose the shorter, the smaller of those 2. And it turns out that 748 plus 402 is smaller than 494 plus 669, so Boise is going to lose out. Okay? So now the shortest path from the West Coast to the East Coast, the shortest path from the West Coast to Casper is San Francisco, Salt Lake, Casper, and it's 1150 miles. Okay, and now we'll repeat this at Denver, Albuquerque, and El Paso. Denver is, again, not very interesting. There's only one way. In Albuquerque, though, we have three numbers to compare. 748 plus 609, that's if you came from Salt Lake. 275 plus 576, that's if you came from Vegas. And 528 plus 452, that's if you came through Tucson, Arizona. Okay, so if we do those comparisons, and then we select the shortest path up to that point, we arrive at this state. So this process of adding the shortest path up to a particular state with a one-day path, and then comparing all of the paths that arrive at a given destination day city, is called an add, compare, select. So we eliminate the losers, we keep the winners, and the winning paths, the paths that are labeled there with the arrows, those are known as survivor paths because they survived the ACS elimination. And you can already see that the best path from the West Coast to the East Coast doesn't go through Boise. So even though we had hypothesized that in order to do some early elimination, it turned out not to be true. Okay? Notice also that even though I gave the green crayon answer for Boise, we really didn't need to know exactly what that answer was in order to eliminate Newport and San Francisco. Okay? We just know that that path has to exist. We don't know what it is, but the fact that we know that it has to exist and it won't change by how we get to Boise allows us to do some early elimination, and that's the key idea of the Viterbi algorithm. So now we will repeat this again for the destinations, day 3 destination cities. For example, start in Pierre and compare how you could get there from either Denver or Casper through the add, compare, select, and repeat it at Lincoln, Amarillo, and San Antonio. And then we would move on to Minneapolis, Kansas City, Fort Smith, Houston, etc., all the way across the country. So if you do that, this is the result. And at the end of this 7 days of travel, potentially, or planning these 7 days of travel, you would see that we'd have 4 survivors at the East Coast, 1 at MIT or Boston, 1 in Washington, 1 in Wilmington, 1 in Daytona Beach. And if you compare the total mileage associated with each of those cities and those survivor paths, those are the shortest ways to go from the West Coast to each of those cities. And so clearly the shortest path from the West Coast to any city on the East Coast goes from or terminates in Daytona Beach. So the last step of the Viterbi algorithm is to look at the survivor on the East Coast that has the smallest distance or metric. So in this case it's Daytona Beach, and the metric is 2658. And the last step is what's called a traceback or traceback and decode operation. And so you want to know the shortest path or the specific legs of the path. You just look backwards. So you start in Daytona Beach, you look back and you say, well, we came from Tallahassee. You look back from Tallahassee, well, we came from New Orleans. We look back, we came from Houston, etc. And you find out that you started at USC. So now we know that the shortest path, in fact, travels from USC to Daytona Beach. Okay? So this algorithm was first introduced to the community by Dr. Andrew Viterbi, our own Andrew Viterbi, first published in 1968. This has been a revolutionary algorithm in the field of digital communications. It's ubiquitous in digital communication modems. And so it's really just based on these very simple ideas of eliminating options as early as possible using this principle of dynamic programming. And then another key innovation which is critical and is unique to the Viterbi algorithm, was critical for the early development and deployment of the technology, is this method of storing the winners as you go, so that in order to figure out the best path, you just do this trace back and decode. That's a very unique property of the Viterbi algorithm.
So welcome back after watching that video. I hope by now you would have understood the Viterbi algorithm a little better. So you saw in the video how the Viterbi algorithm was explained in terms of traveling from one city in the United States west coast to another city, let's say in the east coast, and trying to find out the shortest path iteratively at the end of each step or each day. So the same thing is happening. We are traveling through the trellis and we are trying to find out the shortest path, where the path is measured in terms of the Hamming distances. Okay, so you find the shortest path, you keep the shortest one and discard the other possibilities, and then you find eventually the shortest path, and then you just look back through the shortest path to find out the original message which was sent. So that is the Viterbi algorithm for you. So now moving on with the convolutional coding part. So we'll do an example for convolutional coding. So let's consider a convolutional encoder which is defined by this. So Vn1 is un modulo 2 add of un minus 2, and Vn2 is un minus 1 modulo 2 addition un minus 2. So draw a shift register implementation for this encoder, draw a state diagram for this encoder, draw a trellis diagram for this encoder from T0 to T4. So as you can see, you have two outputs. So it is a example of your k, or rather sorry, your n is 2 here. Okay, and you have three shift registers, un minus 1, un minus 2. So basically your capital K is 3 here. Okay, and I think just from the information given here, you can predict that your input is 1 bit. Okay, or in other words, your small k is 1. Okay, so this is how your encoder would look like. So you have the input which is coming here. Okay, to directly to the un register, and then you have un minus 1 and un minus 2. So everything is shifted in this direction, and then your vn1 was un plus un minus 2. So you just take out two arrows from un and un minus 2, do a modulo 2 add, and then this is your vn1, which is basically un modulo 2 addition un minus 2, and your vn2, as the example says, it is un minus 1 modulo 2 add un minus 2. So you take out two outputs from here, and then those two are getting modulo 2 added, and you have vn2 as un minus 1 plus un minus 2, and therefore this is your encoder, and you can now easily work out the state diagram like this. So just consider un minus 1 and un minus 2 as your state. So 0 0 is the initial state, and then here is your un. If the input is 0, then just find out what will be your vn1 and vn2 according to the equations given there. So vn1 is un plus un minus 2, so this will be 0, and vn2 is un minus 1 plus un minus 2, so this will be 0 again. So if you are in state 0 0, then if your input is 0, then you remain in the state 0 0, because this will be shifted one place. So this will be 0 and this will be 0. So you remain in the state 0 0 with an output 0 0. Okay, so this is the solid line for input 0. Now if your input is 1, then you can also figure it out it will be going to the state 1 0 with an output 1 0, and in this way you can just work out the entire state diagram. Okay, and then this will be the trellis. Once you get the state diagram, just drawing the trellis is easy, and it was said in the problem definition that you have to draw the trellis for 4 time periods. So from t0 to t4. Okay, so t0 to t4 you are drawing the trellis. So t0, t1, t2, t3 and t4. So this trellis can be easily drawn from this state diagram. Once you get the state diagram, you know that if you are at this stage, then the two possible outputs will be either the same 0 0 or 1 0. Okay, so that's what is happening here. You can go to, or you can remain at A, or you can go to B. From B you can go to C or D. From C you can go to A and B, and from D you can go to C or remain in D. So in this way you can just work out and draw the trellis diagram from the state diagram. Okay, so I will stop here today, and I will see you in the next video lecture. So this concludes um, the entire error correcting codes for you. So in the next video lecture we will start OFDM. Okay, so that's it for this video lecture. I will see you in the next one. Thank you.